Hello friends, I am Dr.V Deshpande, Head Department of Physics, Shivaji Arts, Commerce and Science College Kannad. Now this is Synchrocyclotron. Now in cyclotron there are certain limitations that is called as relativistic limitations. To overcome these relativistic limitations of cyclotron, Lawrence built a frequency modulated cyclotron. This machine used the principle of phase stable orbits. The loss of resonance caused by the relativistic increase in mass in cyclotron can be balanced by resonance condition. For non-relativistic mass, the frequency is given by n is equal to 1 upon t, which is equal to hq upon 2 pi m. The relation for frequency of relativistic mass is n is equal to hq under root of 1 minus v square upon c square divided by twice pi m0, because m is replaced by relativistic mass, m0 under root 1 minus divided by under root 1 minus v square upon c square. The decrease in ion frequency can be represented by increasing the field strength H at such a rate that the product of H under root of 1 minus v square upon c square remains constant, or by gradually decreasing the frequency of applied electric field. Now, Wechsler and Macmillan pointed out that by increasing the magnetic field or by reducing the frequency of the alternating potential, or both, the radius of orbit of ions could be made to expand and the energy to increase. The machine where electric field frequency is kept fixed and magnetic field is varied is known as synchrotron, and the machine where magnetic field is kept fixed and the frequency is varied is known as synchrocyclotron or frequency modulated cyclotron. Now consider construction of synchrocyclotron. These two are magnetic poles and here is vacuum. Instead of two D's, here we use one D like this. This is single D. In cyclotron, we use two D's. A synchrocyclotron consists of only one D placed in a vacuum chamber between the poles of an electromagnet as shown in figure. Instead of the second D, opposite the opening of the D, there is a depth sheet connected to the earth. The alternating potential difference is applied between the Ds and the sheet. An advantage of using single Ds is that it leaves sufficient space in the vacuum chamber for ion source and the target. The shape of the pole pieces of the magnet is made up of a suitable shape such that the field decreases outward from the center. This is done to ensure good focusing of the accelerated ions. Now next one is Betatron. Betatron is a device to accelerate electron beta particle to very high energies. It was constructed by D.W. Crest. The action of Betatron depends upon the principle of transformer. Now construction and working. A Betatron consists of a donut shaped vacuum chamber placed between the poles pieces of an electromagnet. The electromagnet is energized by an alternating pulse current. The magnet produces a strong magnetic field in the donut. The electrons are produced by the electron gun. They are allowed to move in circular orbit of constant radius in the vacuum chamber as shown in figure. The field varies slowly as compared to the frequency of revolution of the electron in the equilibrium orbit. The donut-shaped vacuum chamber, the varying magnetic field acting parallel to the axis of the vacuum tube, produces two effects on the electron. These are changing flux due to the electromagnet, produces the induced EMF, which is responsible for the acceleration of the electron, and the field of magnet bends the path of the electrons in circular path in the chamber and confine them to the region of changing flux. Now consider the electron moving in a orbit of radius r. The magnetic flux linked through the orbit phi. The flux increases at the rate of d phi by dt, and the induced EMF E is equal to minus of d phi by dt. Let charge be the E. Thus, work done on the electron is given by E into E, which is equal to minus of E d phi by dt. Let F be the tangential force acting on the orbit of the electron. The path length of for one revolution is 2 pi r. Therefore, the work done of the electron in one revolution is equal to force into displacement, that is F into 2 pi r. F into 2 pi r, which is equal to minus of E d phi by dt, or F is equal to minus of E divided by 2 pi r d phi by dt. When velocity of the electron increases, the frequency F will try to increase the radius of the orbit. Due to presence of magnetic flux perpendicular to the plane of the electron orbit, the electron will experience a radial force inward, which is given by capital B E into V, which is equal to m square by r, that is centripetal force. Here V is the velocity of the electron and mass is the mass of m is the mass of the electron and B is magnetic field. Therefore, momentum of the electron mv is equal to per. From Newton's second law, F is equal to dt of mv, which is equal to er dB by dt. To maintain the constant radius of the orbit, the value of F given in equation 3 and 6 must be numerically equal. E upon 2 pi r d phi by dt is equal to er into d pi by dt, or d phi is equal to 2 pi r square dB. Now integrating from 0 to phi, we get phi is equal to 2 pi r square into B. If a uniform magnetic field P acts over the area pi r square, the magnetic flux phi is equal to 2 pi square B must be twice the flux enclosed by the orbit. If magnetic field were to uniform over the area, the equation 7 represents the condition under which Betatron works and called as Betatron condition. The flux distribution can be obtained by the special pole pieces where the magnetic field is greater at the center of the orbit than at its circumference. The iron is laminated because the induced potential is proportional to the rate of change of magnetic flux. Electrons from the electron gun are injected into the chamber. The electrons are injected at the moment when the magnetic field is just rising from its zero value in the first quarter cycle. The increasing magnetic field induces a potential within the donut of the vacuum chamber and increases the energy of the electron. The electrons are allowed to move in a circular orbit, and the increasing magnetic field keeps them moving in the stable orbit. When the magnetic field has reached its maximum value, the electrons are pulled out of their stable orbit, either strike a suitable target or emerge out of the machine. The high energy of the electron from Betatron is used to produce X-rays also. If the electrons are not ejected out at the moment when the magnetic field is maximum, then the magnetic field starts decreasing and the electrons will start slowing down. To avoid this, electrons are ejected out of the stable orbit at a peak value of magnetic